Well, it's a pleasure to be here. I have to say, I am quite certain of one thing. I am for sure the person in the audience who knows the least about FRBs. So this is very much a cultural exchange. I'm coming from originally being interested in quite a different problem, which was trying to make electromagnetic counterparts out of black holes. And that's when I met Chiara, who had this really interesting idea of trying to apply the same mechanism to FRBs. So we'll talk about that a little bit, but I'm going to be more in the theoretical space and talk about other mechanisms that we haven't really fought through in great detail in the hopes that there are other people out there who might have some good ideas on this. So the idea of the black hole battery is really that it is a novel way to light up black holes. And all you really need in order to make this happen is some basic elements. You need an event horizon, some magnets, and some motion. So I'm going to describe how we initially implemented this idea, but I think that it has much more general application. And this is a series of papers with a lot of interesting people involved. And the reason why we were originally interested in it is if you think about black hole neutron star binaries, many people think that this is going to be a very bright, energetic event on the time of merger, particularly with interest in something like the LIGO detections, which is end state, a catastrophic event, but it's actually not the case. Most black holes are going to swallow their neutron stars whole, completely intact, and there will not be an electromagnetic counterpart. It's underappreciated that you have to have a very small black hole, actually, to have enough tidal disruption to destroy the neutron star. So this might be, at the time that we're working on it, one of the only ways you could even aspire to have a counterpart. And then I loved Chiara's idea of trying to apply this to FRBs. So it's a very basic idea that if you have a magnet, in this case the neutron star, which is transporting in an incredibly large magnetic field, if you wave a magnet around, you know that you can actually turn on a light bulb, right? This is a beautiful result due to Faraday, that waving magnetic fields, changing magnetic fields create electrical fields. And so we devised a simple circuit. And of course, this has been done in many other contexts, especially actually, and Roger Blandford put a lot of these ideas, was the first to really land similar ideas of twisting magnetic fields and creating electronic circuits. But what you really have is a little circuit diagram you can draw where the neutron star is like a resistor, the black hole is the locus of, across the horizon, what we call the battery, and the magnetic field lines of the neutron star provides the wires, and then the neutron star provides the current to actually light this circuit up. So you have all the elements of a circuit. Technically, if you're really into E&M, you would probably call this a unipolar inductor. I don't know, but I just didn't think it sounded as good as a black hole battery, to be completely honest. Okay, and so we do these beautiful calculations in these very clean systems with no atoms and no electrons. And so I have to say, the first thing to emphasize is that we are working totally in vacuum, because that was the only thing we knew how to do in pen and paper. And we're able to do a lot of these great calculations, but the kind of work that Andre was talking about, where you have all of this sophisticated machinery, is still would need to be done to have a better understanding of exactly what the emission mechanisms are. But the simple idea is that you have a potential drop across the black hole because of the interleaving magnetic fields, and the motion through the magnetic fields causing a motional EMF, and therefore electric field lines. And you can calculate back of the envelope, although we try to do it fully relativistically, and we can, actually amazingly in certain settings. But back of the envelope, what the walk away you should really have is how the power scales with different things. And roughly you anticipate that the power that you would be able to get just by calculating what is the potential drop across the circuit, and given that the current is kind of the potential drop over the resistance, how would it scale with the different physical inputs? And the most important is that it scales with the magnetic field squared. So we were really trying to maximize large magnetic fields because in our original interest, we're looking at very distant objects, large cosmological scales with LIGO in particular, and so you really need a lot of power if you're going to see things far out like that. And so, not to take this too seriously, but we cranked up the magnetic field maximally, just like what is the absolute max you could possibly aspire to. So suppose the magnetic field being transported in from the neutron star is 10 to the 16 Gauss. A dipole magnetic field from the neutron star drops off as 1 over r cubed. So if it goes like b squared, it drops off like 1 over r to the 6. So that means any distance from the neutron star, it plunges dramatically. And so it's only in the final millisecond of a merger that you would expect to get the largest powers out. And that's what we were originally looking for. But I think now that so much more work has been done in this area, I think we could aim considerably lower. And that's interesting in terms of the radio, because then we don't have to be in the final fraction of a second. So the drawbacks of being in the final fraction of a second have already been raised by other speakers. It's a cataclysmic event. You're not going to have other repeaters. And if indeed they're all repeating, which sounds like it's still an open question, is not ideal, that would be the end of the system. You might have a post-merger incident, but that would be it. You're not going to have these repetitions on scales of days. And of course, there's a rates problem. If you're looking at the final millisecond, there's clearly a rates problem. So nobody ever was saying, oh, we're going to make as many of these as you would want to justify all of the FRBs we see. It would definitely be kind of a small subclass. But the lower you're willing to drop the energy and the further out you're willing to start looking for something like this, then you have longer lived binary systems and the rates start to go up and you have the possibility for repetitions. So I think that's something we should reinvestigate. Now, as I said, all we've argued is theoretically what would the power be of the system and does it have interesting numerology. But if you want to do the detailed study of what is the actual light bulb, what are the emissions mechanisms that you would see, and how do you generate the different wave bands? And that requires, I think, much more sophisticated analysis than what we've done. We've done sufficient studies. Well, we know we have synchrocurvature radiation. That's going to be very high energy. You might have something like a fireball, which would become opaque for a period of time and would be more high energy. And the idea of having some kind of coherent process to generate radio emission is certainly within the realm of what you would think is plausible, because you're really emulating a lot of the conditions that you have for a pulsar. I don't want you to pay too much attention to this specific study, but this is just the idea that, well, if we did have some kind of coherent emission, the timescales are interesting for at least the first kind of group of FRBs that were coming out. But what I want to point out more than the specifics of this is if you think about the original setup, what you have is a black hole moving through a magnetic field of a neutron star. And that is setting a bunch of timescales. That's really all you need, is motion through a magnetic field. It's setting a timescale, which is the orbital timescale of the system. Did I skip past my slide with my... No, maybe it's coming up. No, I did. I'm going to go back a second because I seem to have skipped past one slide that I want to talk about. Okay, this one. The orbital timescale, but you also have the spin period. And as was raised for double neutron stars, by the time you're looking at these things, you have a lot of precession of the spin of the bodies involved. And so that sets another really interesting timescale. And it's very sensitive to where you're looking in the orbit. So again, initially we were imagining, well, first what has to happen is you have to enter the light cylinder of the magnetic field of the neutron star, meaning that if the neutron star has some spin, you have to be close enough that the field lines remain closed, that it wouldn't require faster than light behavior of the field lines to stay closed, because beyond that they'll just open up and you're not going to make a closed circuit. So the first chance for a neutron star that's spinning like once per second that you're going to enter in and be able to make a closed circuit is at about 1,000 Schwarzschild radii or so, and we're standardizing, just for the sake of argument, to a 10 solar mass black hole. And so if you could see the signal right then, right when you enter, then you have 20 years to look for this. And we didn't really consider that because we were wanting to have such huge output in the energy. 1,000 times the Schwarzschild radius means you're suppressed by a factor of 10 to the 6. It's 10 to the 3 squared. What did I say? 10 to the 6. So like 10 to the 18. So you're really suppressed. You're really suppressed in that power. But if you're willing to consider powers in the 10 to the 30 some ergs to the high 30s before you're interested in the 10 to the 46 ergs, 10 to the 49, then you can actually start much further out. And I think that that's something that would be worth revisiting. Now, sorry, I was mid-talking about the different emission mechanisms. So we know you have synchrocurvature radiation from just particles from the magnetosphere traveling along the curved lines and all of these different emission mechanisms. And so you would anticipate a multi-messenger kind of a signal, something that would have other complementary spectra that you could look for. So what is the takeaway so far is that black hole neutron stars have at least some of the elements you would anticipate to be able to generate something like a very small subclass of FRBs. The time scale is very solid in the sense that part of it is set by the gravitational wave losses, because that's what sets the orbital time scale and the in spiral. The maximum power, you know, is set by the neutron star magnetic field. So you have an opportunity, I think, to consider looking for repeaters in a different way. But another thing I want to emphasize, which we sort of did subsequently, is it's not the only effect that you have from a black hole in a magnetic field. You actually can charge up black holes in magnetic fields. And I think this is something that's very underappreciated. A lot of people believe that you can't possibly have significant charge in a black hole because the electromagnetic force is so strong that you would instantaneously discharge. That is not the case in the presence of a magnetic field. In the presence of a magnetic field, for example, a spinning black hole actually will draw charge as its low energy ground state. It will have a preference to acquire charge, to kill the electric field that it has created precisely because it's spinning in a magnetic field. And this dates back to Bob Wald. It's actually a really gorgeous result. I'm very short on time. I thought for sure I was going to go under, so I'm just going to plow through it. It's a gorgeous result. It's like a 4-page paper. It's one of the finest papers I've ever read in my life. And it proves that the amount of charge you would pick up is directly proportional to the spin of the black hole and the strength of the magnetic field in which it is submerged. And I really want you to think about this. Actually, let me just jump ahead in terms of the no-hair theorem. A lot of people will look very quizzical when you say this because we've all learned that black holes have no hair, right? It's one of the first things that was proven by Penrose and other people, and that it should discharge instantaneously. Actually, these things are not true. The no-hair theorem, if cautiously stated, says that the only magnetic field a black hole can support is consistent with a monopole of charge. If I have a monopole of charge on a spinning black hole, it is absolutely consistent with the no-hair theorems for it to have its own self-sustaining magnetic field. And so the point I want to make is that what you've basically made is literally another pulsar. You've put charge on the black hole. It is now a spinning magnetic dipole. The magnetic field will directly scale with whatever field it's submerged in. In this case, we're imagining a paired neutron star. And you could also thereby imagine that it would create its own magnetosphere and begin to emulate the behavior of a pulsar. It would, however, be likely more erratic. It wouldn't have all of the key signatures we use to search for pulsars because it would have this large precession, and because unless if you pull that neutron star away, just pretend, it would very quickly then discharge, right, and shed its magnetic field. So it has to be in the presence of a magnetic field, and if it's in spiraling, that magnetic field feels stronger and stronger, and therefore the charge goes up and up. So it's not this consistent, perfect clock that you would expect to be looking for if you were looking for a pulsar. And so we can estimate the kind of power that comes out of this, but the point is this is a different mechanism for creating luminosity in all of these various channels. And even more lately, what we've been thinking about is, put aside the binary, because what is the binary really doing for you? It's very interesting because we were interested in gravitational waves, obviously, and it's very interesting because we know they're out there and we know neutron stars have large magnetic fields, although we could argue about whether or not they maintain them at such late stage in spiral, that the magnetic fields might decay by then. But more interestingly, a black hole moving or spinning through any magnetic field will have these properties. It will create electric fields in nearby circuits, and it will charge up. So that means, and this is something we've been calculating recently, a boosted black hole passing through the magnetic field, for instance, in the galactic center, will acquire charge and will create electric fields. If it's spinning and boosting, even more so. And it's hard to think of regions in which there are large magnetic fields. That's why the neutron star was so valuable, because what it was providing was transporting in this enormous field. But there are other settings in which you might have an interesting enough magnetic field that you could see these similar effects. So the bare elements, again, are just the motion, the event horizon, and the magnetic field that allow this to happen. Okay, so what's the takeaway? I'm determined to say this in 2 seconds. Takeaway is that you could create something like a black hole pulsar and have an oddball FRB, but I do think that with some of these new ideas generalizing the idea of the black hole battery, that we have the opportunity to revisit this in different settings and begin to look at the timescales. Thank you.